All right, good afternoon, students. 16th of August, 2022. This is our third lecture, if I'm correct, for ICN 300S. And we'll be essentially covering three-phase balance loads. I did put single phase there because we do touch on it, but predominantly it's all going to be three-phase balance loads. And circuits, so to say. But I'm still deciding whether I'll include circuits, which I included last semester. But I might not. Okay, so let's just kind of move on here. Okay, so like I said to you, I'll be always just showing you where we are. So we're on section 2 now currently. And the first 3 sections will essentially be your first class test if you are looking for scope. Anything what's covered through the lectures and your notes will obviously be covered. Another thing is, I wonder if I can have, depending how far I get, which I highly doubt, if Ms. Makuru was going to have an on-campus session, I can possibly have one as well. But I mean, that's going to isolate some other people. But obviously, that's up to discussion. But let me see how far I get with the content. And hopefully, on the week before the holiday was a holiday, is that week from the 12th of September to the 16th. Yeah, that's the holiday. But nevertheless, I did give you your class test date, and that's on the 19th of the 20th of September, which is the Tuesday during class time at 12 o'clock, and that's at on the Tuesday. Cool. It's at 12 to 2. So the first 3 chapters, as you see there, or sections rather. I do want to make you aware that this particular chapter has no prescribed textbook, so it's just some notes, some tutorials, some exercises. It's just quite a few. I found new ones which I want to actually have a part of, but whatever we cover here will obviously give you an idea of what's expected of you. Okay, cool. So then after that, we have arguably 4 more sections or 3 more depending on time. And this, by the way, is my favorite section. Okay, so what I typically did when I introduced electrotechnology was talking about the context of this particular subject. But I didn't feel it relevant at the time to introduce this because typically 3-phase would have been it's typically the first chapter, but I want to provide some AC network analysis as well, especially the mesh and nodal techniques as well. So anyway, this is the context of subject. So in the previous subject, what we looked at was just some more fundamentals type situations, meaning some new ideas, concepts, and the graduation from DC to AC. So you essentially learn about you taught DC, and then eventually you move on to more AC. And the rest of, in fact, the whole of electrotechnology 3 is essentially it's AC. So most of your analysis will be within the AC domain. But there is DC machines, which is the generator motor part, which obviously, but I'll get to it now. So what we look at in this particular subject is electrical machines, right? And it's classified into 2 types. At that level, it's whether it be static or rotating, and the static would obviously be a transformer. Transformer doesn't do anything, doesn't move at all. Obviously, there is like a sound. And then the rotating elements, we've got it's bifurcated into 2 sections, which is the DC machines, the generated motor, which we will look at. And the AC machines, we look at the synchronous type and the asynchronous type. The asynchronous type is essentially induction motors you guys are aware of. We've briefly touched that on Electro 2 in terms of the energy transfer or power flow within the motor. But we will obviously, in this semester, we'll look at the actual circuit involved to model the induction motor. Then on the synchronous side, is where we actually go into your alternator and motor. Mostly three-phase, not the single-phase element of it. So that's the general idea. And then within the static part as well, we look at transmission lines, which kind of forms part of power systems. And then lastly, again, we're looking at three-phase mostly. So most things you're going to get, besides the DC part, will be in the context of three-phase. So you have a three-phase alternator, three-phase synchronous motor, if you're going to do that, a three-phase induction motor, three-phase transformer, three-phase transmission line. So that's just important for you to be aware of. So we do a bit of single phase just to get the blood flowing, just to get that general idea. And then obviously when you're getting your tests or your assessments, you're typically be in three-phase. But you'll revise on all of this. Okay. Obviously you might ask why. Because I mean three-phase is the most common way of transmitting AC in terms of power generation. That's the most common method of power generation, transmission, distribution, which we'll talk about now. And also it is essentially designed for for more heavy type machinery, which essentially powered the second industrial revolution. And then obviously electronics came in the third. But anyway, so just quickly talking what a three-phase system is. You guys are obviously slightly aware of it. And it states here it's an electrical distribution method that uses three alternating currents to supply power. I'll touch on that again. The type of distribution is mostly used in the world for transporting power from generating systems to electrical supply grids, onshore and offshore. Like a three-phase circuit is commonly used on large motors, pumps, and other pieces of mechanical equipment. Okay, so this is what a typical distribution system looks like. I could have probably gotten a better figure with values. I had it in the last semester. But anyway, you've got a power plant. You've got transformers stepping up voltages. They're going through transmission lines, get stepped down with more transformers at the substation, and then there's also transformers in the poles, single phase transformers, further step down the three-phase into single phase at the home. So that's the basic one. I'll talk about South Africa's one now, or if you arguably we have one, right, or there's load shedding. What's also important to note, I think there's a cool figure which shows you all the single phase and three phase. Both they kind of joined supplies and voltage and frequency specs worldwide. So what you tend to find, as per usual, the Americans have their own setup. That's on the west, where they have 127 to 60 hertz. And then the three phase are 120 to 220. That's at the green side. Obviously, they also have the 220 and 415. I'm aware that your typical vessels in America is 440 at 60, if I'm correct. And then the east side of the world, where Africa as well, which we are applicable to us, is that we typically at your house at home now, we have like a 240 volt or 239 50 hertz, and then obviously our three phase going from 380 to 415, but particularly 380 50 hertz. So that's just showing an idea of the nominal voltage and frequency of three phase systems. Okay, so before I get onto the marine type side, what again, in talking to the sketch over here, because I don't want to be talking too much. This is just a lot of preamble before we actually start the stuff. But just to give context, I think that's important. Again, this is what our electrical grid looks like. And I'm going to use obviously certain words just to show you that the emphasis of three phase and certain so with three phase, I'm sure you guys we have star and delta, which we will talk on. We are alternators typically connected in star, and that produces a voltage of 22 kVA. That is connected to a step-up transformer, which steps up the voltage from 22 kVA to 400 or 765, depending on the distance. So that transformer is typically connected in delta to star. That's your typical step-up configuration. And then that gets further, depending how far it goes to the power station. It gets further stepped down, and it could be at a substation from 400 to 132. And then it gets further step down. They're all delta star essentially, which I find quite strange, but nevertheless, to 11 kVA, and then another substation to around 380. And then what happens is that whether your factory or house, you'll be connecting either to a single phase or three phase. I remember I had to go help my neighbor once because they couldn't get their readings. This was an elderly couple, and yeah, I noticed that they have a three-phase supply. You know, they can actually run more power tools. I know some people have factories around, they typically need like a three-phase supply. And well, your typical home is all single phase. And over there, obviously, depending on the industry, you can obviously connect for whatever voltage you need. And it kind of explains what I just said there. Yes, but we are not onshore. We are offshore, and that is what. Well, this is I think a hybrid type system would look like. And I think what's important for me here, for you to take away, besides just doing the calculations, to obviously understand, you know, there are certain parameters which goes with electrical grid on board. And there are things like basically understanding from the diesel engine to your actual loads, how does the electrical energy or grid work? I think that's important as a second and chief engineer. It's a very complicated circuit. So I am aware that there is a change now going from your conventional type, if you see on the right, to more electric hybrid propulsion. So obviously that further accentuates the importance of understanding electrical both at the heavy current and low current level. So yeah, this is just a schematic of one of them, which I'll talk to now. Just give me a second quickly. Moving along, don't be talking too much. Yeah, so this I got from a paper published by Kumar and Zar et al. And it just talks about a review of maritime microgrids. Essentially, it's a nice, good paper. I'm not sure. I'm still thinking if I'm going to have it as part of your second assignment for the IEEE 45 standard. But depending on which vessel you are, you have to be cognizant that it will have a different, I think that's what I'm looking for, electrical system architecture, right? So this is one type of architecture for, there's this four gensets. Whereas if you look at this one, but I think the core of this particular paper, they're mostly focused on electrical propulsion type systems. And I want to engage with some of the students once I'm just completed this first part. So if you look at the thing on the left, do you have to know this? No, but it's, like I said to you, just to provide some preamble in terms of what we're going to be doing. So you've got a generator, a three-phase synchronous generator, producing 690 volts at 60 hertz. Then you guys can see my mouse. Then we've got a single-phase transformer over there, stepping it down to 440 at 60 hertz. Over here, you'll see is a three-phase transformer. This is transformers over here. And over here, what is over here? These are frequency converters, diodes, and a capacitor. Because typically producing AC, and to control the motor, it's a lot easier to control motor with DC. However, you can control with AC, but DC is a bit easier. This is for electrical propulsion. On a cruise ship, according to them, this is a typical architecture, and you can see it's a combination of AC and DC with your frequency converters all over here with and with the converters you have some rectification, but I mean just as an overview, they need 11 kVA, so they need a lot more volts. Again, here's more architecture, and this is to do with a factory type vessel, and I think that's to do with like a fishing type vessel where they, you know, it's quite indigenous to us, and that's what a typical or electrical propulsion kind of grid. You've got your both thrusters on, but they power directly from the gen. It's shaft power and steering of pods. I'm not sure. Okay, well, we'll talk about it now. And then directly on there from the generator. Then we have these single phase transformers, and then we convert it to power. I think that's the main propulsion over there. And then here's for an icebreaker. You can see they also need more power, around with 11 kVA, and the ball thrusters are directly coupled there. And obviously here you've got a bit of your frequency converter types. Once again, this is just extra information, but just to show you, I think as an engineer, one needs to be, or specifically a marine engineer, when you go on a different ship, the architecture is different. I think that's what's important. And understanding three-phase and AC obviously will provide you with a broader scope. You're free to download the paperwork and share it with if you want to have a read. And then just to show you again another point. I mean, we're not doing MEK electrical here, but if you look at one's LNG tanker, the one with the spheres over there. I'm not sure how common that is here. If you guys, because I know you guys are typically on container ships. It's got a different type. Essentially, it's all the same. You got your generators producing volts at 60 hertz, and then all step down. Your single phase loads will be over here, and these are all electrical propulsion system types, just by the way. And then this is for a reefer container shop, and you can see over here on top we've got 1, 2, 3, 4, 5. I think it's a backup generator, if I'm correct. There's 4 generators, or their own ratings, obviously at it producing 11 kV at 60 hertz, and that gets stepped down into 440. So obviously the container loads can vary depending on what it is, but I think it says an M there, so it's probably some motor or whatever. But obviously it's not only that. And on board there are several types of equipments, and I think I just listed a few. Obviously, three-phase induction motor is the most obvious one. That's powering your compressors, your pumps. You've got a synchronous generator. Obviously, that's the one producing electricity on board, which is coupled to your engine. You've got transformer, obviously, your transmission lines, and then I'm not sure. You guys probably won't see a lot of DC motors or generators, but that might become a thing of the future. I will share with you a paper which talks about, but I'll show it to you once we've done with the lecture. Just someone must remind me on DC grid systems for ships, as an alternative. So now I'd like to open the floor before we start, with the official element of the lecture, about your experience about architectures on board. Mr. Board, do you want to say something regarding this? Your experience with, you mentioned something.
I'm probably wrong, but I think it's because it's 2 separate transformers there, the 3-phase transformers for the propulsion and then the single phase for the actual steering of the pod.
Yeah, sure. Cool. Yeah, that's the idea. Yeah, that's cool. I'd like to have a question. So we just discussed it briefly on the group, but in terms of percentage, I mean, in your experience, and this is for everyone, is most companies moving to hybrid propulsion, or are they still in a I guess in a arguably stone age? There's still the standard diesel propulsion. Can you just share your experience with propulsion? With those two. Anyway, Mr. Board, you want to start it off? Where are we going to in terms of the electrical architecture of ships? Yeah.
In my limited experience, it's just the big ships that don't need to maneuver and don't have to worry about crew and passenger comfort. The directly coupled slow-speed diesel is still the most efficient way of getting the ship to move. So then, what's it called? The cruise ships and things that have to maneuver in tight situations and have to consider vibrations and things like that, then they use a bunch of small engines.
No. I appreciate that. Yeah, I didn't even know that. That makes sense. Let's see, Mr. Assa, Mr. Duplessis, maybe. Get some guys to talk. James. Anyone up to sharing experience with electrical architecture? What is your experience in terms on board? Let me get more people here. Ms. Duba, Muda, Zimkita. she's currently. What's your experience with? What can you add? Is Nusipo easier? PJ, nothing, guys. You have nothing today. Okay, cool. Oh, yeah, no. Oh, yes. How's it?
So it's Mongo here.
Mr. Mongo. Yeah. You.
Yeah, they usually use it similar to what the previous guy just said. They're using these electrical motors on like small ships, and where there's something called dynamic positioning, whereby
Yes.
a ship has to stand in a specific place and doesn't change direction. So they'll be using those motors to be monitored by different systems, so that they can stand in one space and not drift or just swirl around,
Yeah.
just stand in one place. So they're using those different motors, those small motors. So, but in big ships, that's usually not the case unless you're talking about a cruise ship or whatever.
Yeah, no, sure. Thanks for that. Mr. Lowe, your hand is up.
Good day, sir. Can you hear me?
Yes, loud and clear, man.
Okay. So I work in a little bit different industry than the commercial. We're moving more towards hybrid vessels in the sense of power generations. So we have battery banks, and
Nice.
by that, when there's peak demands, we can use from our battery bank and not start up another generator. And in that way, we reduce running costs and also saving on fuel and all that kind of thing. Same what we're doing with houses at the moment. So
yes, no, sure. I get that. Yeah. Cool.
Yeah.
Anyone else? Yeah, anyone else want to add before we move on? Just a discussion, no pressure.
Sir,
Mr. Swanepoel.
Sir, can I ask Mr. Lowe what industry is in?
Oh, yes. Okay. Mr. Lowe. How to charge batteries. That should be not.
At this stage, I can't add too much where I'm working. That's confidential at the moment. A few private projects that I'm busy with. So yeah.
Okay.
Sorry, guys.
No, sure. That's all good. Okay. Yeah. So I think, I'll just show you these architectures. Just on the perspective of that, one must be cognizant of, obviously not on board the same ship all the time, and things are changing, so that you're aware that your understanding of electrical type systems is key, even though you're a mechanical / marine engineer. Nevertheless, we can finally move on. Okay, so why three-phase, right? So, okay, first of all, how we generate three-phase and why three-phase. We'll now obviously touch on it a bit more in more detail when we get to the computations. So three-phase generated typically in a synchronous alternator, and I'm specifically using these words, which you will be doing the analysis on. And we've got coils 120 degrees out of phase, and we have a magnet or electromagnet, whatever, essentially being rotated. That's typically coupled to the shaft, and then we're producing three independent voltages 120 degrees out of phase of each other or displaced. So obviously, this was touched in the previous lecture. So that's how we generated. Not going to go too much in detail with that. And generator we typically use for DC, alternator we use for AC, because it's alternating current. That's the idea. The advantage of three-phase systems, obviously over DC and single phase, is that we require thinner conductors to transmit the same amount of kVA. Obviously, that's the total electrical supply. Some of you guys know what I'm talking about. Some of you guys still need some backdrop on that, which we will cover. Obviously, that's at the same voltage, and it's typically around 25% less in terms of copper. And this also reduces the construction and maintenance costs, which is important if you had to use, your single phase or whatever, or DC. The lighter lines are easy to install, and the sporting starters can be less massive and further apart. In general, most large motors are three-phase because they essentially self-starting and do not require special design or starting circuiting. While most, obviously, you guys go on star and delta starters, depending on how big the motor is. It's got a constant rotor torque, therefore steady machine output, which is important. We need a continuous torque for continuous mechanical power to propel. Typically three-phase machines, this is very true. Both alternators or generators or motors have high efficiencies, ranging from 80 to 95%. It's typically a function of the power factor. Also, three-phase generators can be connected in parallel, which we'll kind of briefly touch on, or alternators to basically supply more power than a single-phase generator. If you wonder what a single-phase generator is, I think your household, your generator at home, you know, those petrol-type generators, unleaded, that's a single-phase generator. I don't think they have a transformer in them to step it down, as far as I know. Okay, so a three-phase system is, just some revision, there's two types of them, how we can configure them, and one is the star or Y connection. I'm not sure what you guys know it as. And what's important here, it looks like doesn't look like a star, it's like three different, well, I guess, what am I thinking about? It looks like a star, I guess, or whatever. I'm thinking this one is like a triangle. Yeah. What's important of the star, okay, what they're saying there, that each end is connected, and there's just two things I want to make you aware, and this particularly in this slide. They're all 120 degrees out of phase, as said before, and we have something called the phase and the line. So the line current is the line in the phase. So the phase would be each individual phase here, so 1, 2, and 3, and the line would be, you know, from that point to that point. What's important here is that the phase current is equal to the line current, because it's a very important thing to know. However, your voltage is √3 times V phase. There is a whole explanation on where the √3 comes from, but when you're dealing with three-phase systems, always be aware that there's going to be a √3 somewhere. I think you guys, if you watch my lecture on three-phase, you've probably you probably know this. So yeah, that's very important with that. Other way to configure it is your delta or mesh connection. It looks like a triangle, and in this case, our voltage is the same, and then our line current and phase current is times by √3. The way I think about star, I think about star as a series circuit where the current is the same throughout, and then our voltage is not. And I think of your delta as a parallel type system where the voltage is the same, where the current obviously is not. They have to multiply by a factor of √3. That means each phases get the same voltage. And obviously the current magnitudes are the same, but they're 120 degrees out of phase. Over here, same current, 120 degrees out of phase, however, and the line voltage is different, I guess. And here are just some comparisons between the two. All I can say, the main differences, what I know, we typically supply with star, and we typically run loads on delta. So that's like a quick one. And just in terms of application base, right? They state their star connections is typically used for both transmission and distribution networks, where delta is typically used for distribution. Star is good for longer distances. That is why you'd find your step-up transformer, it'll be it starts as star and starts at delta, then star at the secondary side to go. Star connections also require less starting current. However, that's a problem with low torque. But on the delta side, it requires a high starting torque. Yeah, so just a rule of thumb, you typically want to supply with star. That's why your transmission lines will be in star, and your alternator. And if you're running on load, it's typically delta. But I mean, there's obviously more understanding with that. Okay, so I'm sure you guys have seen, these things before. Your chiefs. I'm just showing you basic applications. It's all over, just to convince you. That's a star and delta starter, which we use for, I think you guys did do a practical of this during a workshop training. And that's just that's a induction motor nameplate. And on it, you can see a few things like 690 star, 400 delta, 660 star, and all at a certain frequency. They're giving you the power ratings of each one, which you can calculate. They're giving you the revs per minute. This is typically the rotor speed. They're giving you the particular current, and that's the power factor. So I'm just bringing you or bringing to attention that this is all around you on all electrical equipment. So when you see it, you can't say, I don't know what that means. That's what it means. What it means in this case, if you run the motor at a 50 hertz supply and 400 on delta, it will draw so much current at that power factor, and this is questionable, and it will still give you 55 kilowatts of power. So there's a few varieties. I can connect the motors. Obviously, there's a terminal box which is over there. You can connect it with star and delta, and depending on the supply and the connection and frequency, you'll get a different thing. You can see if you have 440 delta, 60 hertz, 63 kilowatts. Just making you aware. This is a transformer nameplate. I did show this to my students last year, and you can actually do some calculation to prove that it's true. But the idea is that you can see there's a high voltage winding, the low voltage winding, and yeah, there's just over here. That's the primary is connected in star. That's the one, and then the secondary is in delta. But I'll revisit this. That's a transformer, another transformer, and yeah, I'm going to come back to all of this. Some more revision in terms of this. What you need to know. We are dealing with RLC circuits, and what's important here is to know that we have R stands for resistor, inductor, and capacitor. And this is just giving you an idea of what the phase angle will be, will it be leading or lagging, right? So I'm not going to talk too much about this, but I just want you to be aware that you must be aware of the concept of leading and lagging. And I actually didn't put it in here. I just realized I missed that. What is important is inductor. This formula over here, your inductor produces an inductive reactance, and the equation for it is X subscript L, lower subscript L. L is 2 pi FL. We're going to be using it a lot, so get comfortable. Obviously, you've touched on it a bit with AC, I think. And then your capacitance 1 over 2 pi FC. Typically, inductors, they lag the supply voltage. The current lags the voltage. So that's in inductive or lagging circuit, where a capacitor will lead. And this will talk to power factor correction, which we will touch on during the course of the next 2 sessions of like this week and next week. What's important here, and you can revisit the slide, we're going to be dealing with complex numbers, so that's not going to change. But if they talk about an inductor, make sure you have plus J17, and if it's a capacitor, it will be negative. So this is very important. A lot of students get confused whether you have inductor or capacitor, but inductor is always plus J, and this is negative 17, negative J. So just be very aware of this. This happens quite often when students confuse it too. And you will see once question starts. All right. So 3-phase we've covered. We've looked at some basic RLC circuit types, and we do some revision on AC power, right? Before we get on to 3-phase. So what typically happens with generator will produce, again, this is all revision, the apparent power, which is rated at volt amps, or particularly kilowatt amps. And that is split into 2 components, right? So the 2 components would be your active power and your reactive power. If you look at the sketch over here, this could be analogous to a generator powering this motor. So the active power is the actual kilowatt, which us engineers should what we look at, and the reactive power. So what the reactive power essentially is, it's the power to maintain the electromagnetic field of the generator. And we obviously don't use the reactive power. It's treated as a loss, and we only use the kilowatt. That's related to the torque coming out. So what it says, the active power and the active, so active bracket working power and the active non-working magnetizing power. The active power performs a useful work for us, and the reactive power does not. It only functions to develop magnetic fields required by inductive devices, because most of the devices we use is electromagnetic induction devices, transformers, motors, and we produce a magnetic field, and then we require energy for the magnetic field. And the equations for them, the parent power is volts times current in volt amps, very important for the units. For your true power is VI cos phi, which is called the power factor. We'll touch on it again. And your reactive power, which is VI sine or phi. And that's called the reactive power. Units VA, W, and VAR for the active power. Very important when you're solving the equations. Okay, so what is the reactive power? Just to really bring it forward again, it's also known as a useless or worthless power. Sometimes they use terminology within the questions. And it says the power that continuously bounces back and forth between the source and load is known as reactive power. Obviously, it's for the magnetic field. And they say the power merely absorbed and return in load due to its reactive properties is referred to as reactive power. I'm just giving a few definitions here. Reactive power represents the energy first stored in the magnetic field and then released, because that's what inductors essentially do, both in the magnetic field or the electrostatic field, in case of inductor and a capacitor. So what's important there, nice red note, the inductor consumes reactive power where capacitor generates reactive power. So just revising all the concepts from electrodes 2. Okay, so some more equations, just the equations again. So there are two ways to obviously do it, but just to further bring it forward again, what these essentially is, the apparent, true, and reactive. There's a relationship between them, and the relationship would be the real power. You can treat it as the horizontal component, and the vertical component would be the reactive power. If you take the hypotenuse or the resultant of the two, you get the apparent power. So apparent power, you can think of it as a total load, and it has two components, would be the reactive power and the real power. What you see over there is the equations for them for three-phase now. So when you see that sign over there, you could replace it with the P. It'll be 3 times the phase voltage. Excuse me. The phase voltage, the phase current times cos theta. But I don't typically use these ones. I use these ones. So for your three-phase power, it's root 3 V line I line cos. For both star and delta, your reactive power root 3 V line I line sine and sine of theta. Your apparent power will be root 3 V line and I line. So if you're looking back at these formulas, the only difference between the single phase formulas is just there's a root 3, and it's called the line voltage. So I've seen some students use this type, which I'm perfectly fine with, but I recommend just sticking with these ones. They don't come in your formula sheet, as far as I know. I'm gonna just check again. This is obviously, you have to kind of know this from the previous subject. All right. So what I wanted to show you here was from an electrical board, and I wanted you guys to actually work out some stuff for me here using those formulas. So let me just take that particular part. So this is one of my students have sent me. This was, I can't really recall when. It's an actual system. Should I just copy and paste these at the bottom here? Just see if you guys can manage. Okay, let me first talk to it, and then yeah. How much can you guys see? Okay. There. Cool. So this is two of them. Well, there's 3 pictures. So this is what it looks like. There's 4 generators over here. What you can see on the power management system, that you can see generator 1 is not connected. Generator 2 is connected. It tells you its system voltage is producing, its RPM is 722 revs per minute, the amount of current it's giving, the kilowatts, the kV, kVA, the VAR, and then your power factor. I'm not sure what this loading is actually representing, how much is actually being used. And generator 3 is offline, hence nothing, some residual current there, and then generator 4 is also connected at that particular voltage with its voltage, that and that. And then further on generator 2, if you click on generator 2, it pops up this thing, and you can actually see the system voltage, the power factor, and all the 3 elements in terms of this. And also shows you the current in each phase. As you can see, typically it's supposed to be the same, but it's not always the case. Even the voltages as well, it's actually giving to you, but they're all within the same region. So what I like you guys to do, using, let me just use this one. Do you guys remember the formulas for this, or should I paste it here? I'll paste it now. Just prepare it for you. I'll need to calculate I wonder. Just paste it over here. Hope you guys can see it. The true power, the reactive power, and the apparent power. I didn't talk about power factor yet, obviously, but I just want to see. So your power factor is cos of whatever, or rather, let me just, what am I doing? Okay, cool. Yeah, so I don't know if you guys can see this, but yeah, some of you guys would know it, some of you guys wouldn't. Some backdrop. Okay, cool. So let's see if they're lying to us. So can you guys calculate for generator 2 and 4 the individual power? So like I said, cos theta is basically the power factor there, the 0.872. Yeah, okay. Is it all clear, guys? Give me some thumbs up. Is there any questions before we move on? Just a quick fun calculation. Any questions, guys? You try to calculate it quickly. Are you guys following? So take the line voltage there, the line current, times by the 0.872, and then let's see if we get that power there. And try it for Q, try it for S. Please. Did you guys get it? Who managed to get it? Mr. Mungo, Mr. Ball, Mr. Mart, Mr. Ashipala. Close, but not exact. Yeah, it shouldn't be exact. Yeah, definitely not exact. Okay, who else did it? Mr. Silver. Little bit off, but yes. Okay, cool. Moda, did you do it? Yes, Mr. Ball.
How to do the sine theta when they give you the power factor, because I thought the power factor given there is cos theta.
Yeah, so you have to. I'll do it now. Okay, so don't worry. Okay, just get yourself down, play around. Okay, cool. So what you're gonna have to do, and obviously this is just a warm up. It's not just so you'll get comfortable with this. I think hearing from Mr. Ball, obviously we want to find the angle first. Yeah, there's many ways to do it. You can just find the angle actually, because your power factor. So obviously some students know is essentially equal to that there. So we can go cos second function 0.872, and we can actually get what psi or theta is, whatever. All right, let me just write at the bottom there. So it's 29.31 degrees. Power √3 times the line voltage, that's 602.38 times the current is 26595.31, and we can times that by cos of 29.31, and we can do the same with Q. Same voltage. Okay, let me just find the answer for that one quickly. See what. Yeah, so never be precise, but for sure, surely that's the calculations the program is designed to use. So it's 28 602.38 times a lot of a big current there, 2695.31 times cos 29.31. Okay, and you get 2452. You guys get the same answer? 157 kilowatt. You guys get that one? Close enough. Yeah. No, okay, cool. I see it. Cool. So yes, they were off, right? I'm not exactly sure why. Maybe it's to do with the loading there. And then you can do the pattern power. Let's just do that one. We'll do 3 times 602.28. Sorry, not 38. Times 2695.31. So quite close. I'm not sure exactly why, but the idea is that you're still getting a good, it's fairly within the range there, 95.31. And you get the rating of it, which is around 2811. Yeah. So maybe this has accounts for maybe some losses or something, or who knows, but still close enough. So yeah, kind of works out well. Delay from real time. Oh, cool. Yeah, that's also possible. Thank you, Mr. Ball. There's many factors, but I mean, the idea is that these values are real. They're not just some fictitious things you learn in the class. All right. Okay, moving on. So I think what I wanted to do here was you could have actually done the same with this over here. So this is a asynchronous generator, which is an induction generator, which I not really want to. So that's my synchronous one. Frequency, nope. You could legit find the the rating. So the rating there's kVA. You can see that one transformer over here, the one on your right, is 2000. And if you were to take the root 3 times your voltage times your current, so if you take root 3 times 11,000 times I think 105. Yeah, so we take, I'll show you now. Where's it on again? Just delete you. So this is for transformer. And you take oh, what am I doing? Guys, I want to do this. So to find the pattern power, because that's what a transformer is rated as, that is there in kVA. You take it for the primary side, the high voltage side, it's root 3 times 11 times 10 to the power 3 times the current there, 440, not 440, sorry, it's 105. What answer do you get? Mr. Ball, Mr. Mongo, Mkita, Mr. Peters. $2,000. Quite close, eh? 2000.52. It's quite close. Yeah. So yeah, that's just to accentuate. Not gonna come in a test or anything, but I mean, excuse me. Again, it's real values, and as an engineer, one needs to be able to look at these values and interpret them for whatever reason, whatever context. Okay, this is some more applications which I put up here. Terms of star and delta. Yeah, going on to power factor. Okay, so you've obviously touched on power factor. You are aware of power factor. You've cut it in those two. We just played with it a bit here. What is the power factor? And the power factor is in essence the ratio between the true power to the total apparent power consumed by an AC electrical equipment. Yeah, and essentially what it is the efficiency of how electrical power is converted into useful work. Probably that's one of the best analogies for a lot of people. And you buy a beer, a Devil's Peak Pale Ale, or a Castle Lager or Black Label, and as they top up your beer mug, you get a bit of foam, and you get some beer and you get some foam. You tell the barman to pour some more so you get rid of that foam. And the analogy is that it's like having real power, having more beer than and the foam, the beer will act as a real power, which is for actual use. And then obviously the foam will act as your reactive power, and the total would be kVA. I'm sure you guys have seen this before somewhere. Black Label has no head, man. Yeah, this. And yeah, and again, it's and in your power factor will be the ratio of it'll be exactly P divided by S, and you get cos of that particular thing. That is essential power factor, only real power. Yeah, Mr. Ball. Yes, this is not actually a true sketch. That kilowatt should be way lower, according to me. And Lays, yeah, they know what they're doing. And another good example, another good analogy. Yeah, you buy the whole bag, you get not even that there. Less than half on the Lays, definitely less than half. This figure was very idealistic for Lays, but you get the idea of what kilowatt kVAR and kVA is. Yeah. But that's two good examples. I think getting idea. So even though your generator is applying 500 kVA, you don't actually get all of it. You get a fraction of it. So for instance, reverting back to a real-time sketch, it's giving out 3, 5, 6, 7, and yeah, we only can consume not the kVA obviously, but you only get 3,000 kilowatts in terms of that power for this particular generator now. So yeah, and it's a power factor 0.8. So it's around 88% efficient in terms of the electrical supply, converting it into actual work to be done. Just as an idea. All right. talked about I already talked about this. Again, what the power factor is, and it's again just the true power divided by the parent power, and more of the same really. And yeah, it's in essence relates the real power to the reactive power. Okay, so there's just some. I want to actually do the calculations here, not there, but it's fine. Just thought I'd do it away. Okay, so this should not be there. So just as a warm up from your John Bird book, before we actually get into so after this, so we're done talking now. We're just going to be solving some questions for the remainder of the lecture. So let's begin with this one. Our warm up problem, example 0. I think let me just put on the whiteboard and then we can begin. Is there any questions so far? You guys finding it interesting? You guys learn anything new besides what you've known already? I'm opening the floor up for 2 minutes here. Where is on the book did you get those questions? It's in the John Bird book. I have to go check for it now. Just give me a moment. But don't worry about it because you're not going to get it. It's not even worth your time. It's just a warm up. So I realize revision is kind of paramount for a lot of the Owens. Well, colleagues rather, not be gender specific or anything, but yeah. A lot of the students need some good revision. It's on, opening the book here, it's on page, what is it? Page 408. Okay. Okay, I'm sure you guys can see this. Cool. All right. So obviously I'm not going to be doing what they do in the way they solve it. It's obviously the way we're going to solve it. Okay, cool. So just like I said, it's a warm up. And I'd appreciate if you could do it, right? So basically we have 3 identical coils. Okay, so I think a resistor and an inductor. It's 10 ohms and that's 42 millihenry. And the first connection would be in star, and it's being supplied by a 415 at 50 hertz source, right? 3 identical coils, always typically 3 identical for balanced load. And what they want is the power dissipated. So the power dissipated in this case would be power √3 VL IL cos. Yeah. So typically say a parent power, reactive power, but in this case they want the true power. Excuse me. All right. So first thing what's important here, we need to find. Let me just make sure this is not something that I actually wanted to do, but okay. Yeah, let me just see. Do they give us our what way, or do they give us our phase, or okay, let me see. First, what you want to do is that our inductor over here is not in ohms, so we have to convert it into inductance reactance, and we have to use 2 pi FL. So again, this is just revision, not even where we need to be. 2 pi times 50 times 42 to the power -3. Mr. Ball, can you give me this answer? 50. So then this will be in ohms now. And that is what we essentially want. Okay, let's get that. What's my inductive reactance? 13.19. Do you guys agree with that? 13.19. What's it? 196. So 13.195. I'm happy with that. Is everyone content with that? Cool. So once you're happy with this, we need to get to this, right? So we have the voltage, right? We don't have the current yet. So that is what we need to work. So we need the voltage, the line voltage, and the line current. And the power factor, we still have to get as well. So that's together. Obviously, we'll talk about it now. So how do we actually get this? We typically work per phase. That's why I'm denoting V phase, I phase, Z phase. We've obviously done this before. And we use complex numbers. Not going to go on the book. So first thing is first, right? In the star connection, your relationships. Your I phase equals your line current. Your V line equals √3 V phase. So we're working per phase, therefore we need our phase voltage. We typically work per phase because we're assuming all the phases are the same, right? That's the idea. So can I get my phase voltage quickly? Just to warm up, get the blood moving. Or can you guys, you get me that? So what's my phase voltage? Fantastic. 239.6. Does everyone concur with that value, with Ms. Duba's value? Are we all happy with that? Guys, are we all there? Are you happy, Mr. Mongo, Simkita, Mudanalo, Desire? Okay, cool. Nice. All right. So like I said, we work with complex numbers. And we all know that voltage is the reference, right? You recall. So what we do now, we're going to have to find our phase current. And it'll be essentially your phase divided your phase voltage divided by your phase impedance. That's what we call Z. Yeah, I've kind of skimmed over that. So you go 239 in complex form on your calculator, and your Z phase, as I said, it's important, is to, now you're going to say 10, because you're dealing with the inductor, it's J, what's it again? 13.195. That's why that is so super important. Once again, if it was a capacitor, you would have had negative J, whatever the value would be. So I hope that's all clear. So let me get that phase, the phase, what do you call it? The phase current. Make sure you do it. Very important. Yep. I'll give everyone a moment. Johan, Mr. Swanepoel's got it. We look at John Bird. John Bird does it a whole different, immature way, basically. Meaning with a more mature, proper way. All right, we'll take a nice short break after this. Mr. Ash has got it. Okay, give it 1 more minute. Right, I think that's enough time. It's 1:15. Okay, cool. So the answer was, sorry about that. The answer was what did you guys get? Sorry, just click on the chat here. 14.472. Move that up. 472 at an angle of 52.84. Okay, what's important here is to look at, because the inductor, it's negative, so therefore it's lagging, right? Just as revision. And this here is our power factor. So remember, your power factor is cos phi of this particular angle. So your current always accompany an angle, and it's 52.84. What it means is that it's 52.84 degrees out of phase or lagging with respect to the voltage over there. So your power factor value, in essence, the actual value is cos, what's it now, 52.84. Oh, going to get the actual value for it. 52.84, it's 0.604 lagging. Very important. You must state that as lagging, because your power factor can be leading. I'm getting 17. I don't know what it is. No, Mr. Mono, check your stuff. We shouldn't be getting 17. It's impossible. I'm just checking the book quickly. The book, 6042 lagging, yeah, 14.5. Cool. Yeah. Once that is done, they've requested for the power dissipated. Power equals root times your V line. Your V line was given as 415. And because it's star, your phase current is equal to your line current. And sorry, your phase current is equal to your line current. And that's 14.472 times this is VL IL times 0.604. And there you can calculate your power dissipated. All right. And if you do that, I'll do it for you quickly. 14.47472. You get 6283.104 watts. Sorry. You found that. Is there any questions, guys? Before you guys, oh, there you go, it's got it. Any questions before you guys do part B? I'll give you guys a few minutes to do part B, and then I'll quickly do it, and then we can go on a nice tea break. Then continue. Any questions, guys? Any clarity? This is the time now. Any questions, guys? Let me just see who's here. Mr. Peters, Tsepo, Mr. Mukali, Mr. Mini, Mr. Sima, Mr. Yengwa, Mr. Nsongo. Any questions? James, any questions? Mr. Silva. Cool. Nice. Okay. Cool. So what I want you guys to do now is do the next part. And it's connected in Delta. So I'll give you guys 3 minutes or so to do it. And then, yeah, I'll do it, and then we'll take a break. And then you'll continue with some more. Yeah, it's going to get fun. It's going to get fun. And you go single phase load, and then do the 3-phase one. Yeah. Okay, cool. Fantastic. Thank you. So guys, do part B. Just now it's connected in Delta. So same procedure and connected in Delta. Okay, 25 past. Let's get it. We can do B. Let me just do B over here. So because we're in delta, our V line is equal to our V phase, and our phase current is our line current is √3 of our phase current. Cool. So once again, we still need to find the current. That's not going to change per phase, but our voltage was 415, and that remains the same because our line voltage is equal to our phase voltage, and we're dividing this by the same impedance, because I mean that hasn't changed, which was 10 plus 13.195. 13.195, and that's your phase current. Okay, so if you're doing that, I'm going to take a shot to it quickly. Calculator must be in complex mode, and you'll get an answer of 25.066 minus 52.843 degrees, right? Obviously a lot different from that. Got more current, and now we need to find the line current, and we just have to multiply that by the 25.066 times √3, and you should get 43.42 amps at the same angle. That doesn't change. All right. I shouldn't put the answer actually, just something there. Should be over there. And to find your power, simply √3, line voltage is 415 times 43.42 times cos of 52.843. Yeah, or you can just find whatever that value was, and then just quickly get that. 415 times 43.42 times cos 52.843. And we get 18.851 kilowatts. Did we all get this? That is left for you. Okay, I think I should probably do that other one first. Okay, cool, nice. So just looking at that, just the power difference, and I think the book nicely articulates it and says that you connected in delta, we get around 3 times more power when connected in star, and also take a line current that is 3 times greater. So quite interesting. For the same arrangement, we get a different kind of setup, and therefore we get more power when we're running on load there. So yes, very interesting. That are just a warm up, and then I'm gonna go on a break. So I'm thinking of actually first doing in keeping with the 3-phase. Yeah, I'll probably do example 3 first. Yeah, because we're in this motion. Yeah, I'll do this. Okay, so what we're gonna do after our coffee break or tea break, we're gonna do this example. Then we're gonna do one where we have multiple loads, right? And then we're gonna do another one with more a 3-phase with multiple loads now. I like this one in particular. And then I think we'll be that'll basically be done for this session. And then we start next session we will do power factor correction, just re-explaining that. And then there's more multiple loads, which I'll give you. This will be for homework. This is actually in a test and exam. And I'll probably, there's a few, obviously when I post up the slides, then you'll see the rest, what you need to practice. So I can let you do this in one lecture, but I decided to split up in 2, 1.5, that just to see how rusty people are. So we're gonna do this one when we get back, and then we'll do probably do 3 more examples when we return for 3-phase. Then you're going to have to go practice. And I'll show you exactly where you should go and practice. And yeah. Okay, guys, so let's have that break. And we can return at, make it a 10-minute break at 22. Make it at 1:45, and then we can proceed with 3-phase single loads. Oh, this is single load. Yeah, okay, cool. We can continue with our 3-phase balance loads, and you'll see what I mean once we've got it all in. Okay, end of session 1.